Hello, my name is Robin, and today I'm going to show you how to solve a second-order differential equation with constant coefficients. So very first thing is we're going to take a look at what that looks like. So this is the general form of the equation, and you'll see here that the constant coefficients are going to be A, B, and C. And this equation is linear because we have our independent variables not being multiplied by anything, they're not to the power of anything. And this equation is also homogeneous because it is equal to 0. If it's equal to a non-zero, it would be non-homogeneous. So it's a pretty easy way to remember that. So the first thing to solving these equations is we have to guess, and we have to make an educated guess to see what would go into these equations that would make it equal to 0. So we're going to go with y equals e to the rt. All right. So what we're going to do is we're going to plug this equation into the general form and see what that comes out to. So in order to do that, we do need y prime and y double prime. So there it is right there. And now we're going to plug it in. So here is it, and here it is in its expanded form. And then you'll notice that each term has a common factor of e to the rt. So what we're going to do is we're going to factor that on the outside and put ar squared plus br plus c on the inside. And then you can also see that we can divide both sides by e to the rt. And then we're going to get ar squared plus br plus c equals 0. This is a very important equation. So what I'm going to do is I'm going to highlight it in my favorite color. And this equation is called the characteristic equation. So this is a very important step to solving these equations. This is the very base of it. So when you start solving these equations, you don't have to plug in the e and the rt. You could just go ahead and write it from here. So let's say your equation was 14y double prime plus 5y prime plus 7y equals to 0. You can just put it directly into its characteristic equation as 14r squared plus 5r plus 7 equals 0. And it's like that for all of them. So it's really easy. There might be some times you have to plug it in, but most of the time you don't have to. So that is that. So when you solve these equations, there are 3 things that are going to happen. There's going to be 3 cases. So let's take a look at those cases. So case 1, we're going to have distinct real roots. And that just means that they're linearly independent and they're not multiples of each other, and they're just 2 different numbers, real numbers. And then for case 2, we have repeated roots where the r is the same. This is just repeated, pretty straightforward. And then we have complex roots. And this is when we start bringing in the imaginary numbers. This little I right here, it's an imaginary number. And it does get pretty complex, not to be funny. So each of these have general solutions. So today I'm just going to show you how to solve for r, and then what we're going to do is we're going to plug that r into these general solutions. So for case 1, pretty straightforward. The general solution is y equals c1 e to the r1t plus c2 e to the r2 plus t. So we're just plugging in this r1 to here and this r2 to here. Pretty straightforward. Next, for the general solution for case 2, we have y equals c1 e to the r1t plus c2t e to the r2t. And I will give you more information on where this t is derived from. So this is really helpful when we have repeated roots because we need them to be different. They need to be linearly independent. And last but not least, the complex root general solution is very long. So you'll see that we have a cosine in here and a sine, and then we have alpha and beta, which comes from this R. All right, so let's do examples. First, we're going to look at case number 1, which is just distinct real roots, okay? So this is a really easy example. We can just factor this equation, but the very first step is to put it into our characteristic equation, which is right there. So our coefficient here is 1, and then this is 5, and then this is 6. And then we're going to factor it. You can do your X method, you can do your box method, whatever works for you, but we're going to factor it. Super easy. R plus 3 times R plus 2. And then we're going to solve for R. So R equals -3 and R equals -2. So now what we're going to do is we're going to just take these R's and plug it into our equation. And the result comes out to this. So that's our solution to this equation. Pretty easy. All right, now let's move on to case 2. So now we're dealing with repeated roots where the R's are equal to each other. So I wrote again the general solution so that we can apply it here. Now I'm going to explain where that t comes from. So I just use the equation y prime minus 10y, y double prime, minus 10y prime plus 25y equals 0. So first things first, we put it into our characteristic equation, and certainly lose by 0. And then we're going to factor it. So it's going to be r minus 5 all to the square. So this is repeating r because if you solve for r, they're both going to be r equals 5, right? And we actually cannot be having that because that won't be linearly independent. And that's what they need to be in order to be a real solution. So we're going to set y1 equal to c1 e5t. And this is just coming from one of the r's. But we need to come up with something else for the second one. So what we're going to do is we're going to do y2 is equal to v of t. And this is just some function of t. It could be any letter, but we just need it to be a function of t, so it's not the same, not just like a regular constant. Otherwise, it's just another y1. So we need to make it something else, and it's still going to be e to the 5t. The question is, where did this t come from? Well, it's something called the reduction of orders, okay? So very first thing, I'm just going to write this equation out. We're just going to simplify it and just call it t. We know it's v of t, but we're just going to call it v to make it easier. There it is. And then what we're going to do is we're going to take the derivative. So the derivative of y2 is going to be y2 prime. And then we have to make sure we're applying our product rule. So we took the derivative of e to the 5t, pulled the 5 out to the front, and we're leaving v normal. And then we're going to add it to just this plus the derivative of v prime. And then we're going to take the derivative again, and then we get this. So this is just this simplified. I also put it in order of the derivatives, so it's descending. It looks better this way, and it's a lot more organized. Right? And then we're going to plug it into y double prime minus 10y prime plus 25y equals 0. So all of these terms are going to be going into this equation. And that whole mess is right here. It's really small, but so this is me just writing it in parentheses, clearly stating which is which. And then in this line, this is where I distribute everything. So you'll notice that we have there are things that can be crossed out. So you'll see we have a positive 10v prime here, and then we have a negative 10v prime there. So we're going to cross those out. And then you'll also see that we have a negative 50v, and then a positive 25v, and a positive 25v. Those all cancel out. So we're also going to cross those out. And then what we're left with is v double prime e to the 5t equals 0. Now, we're going to solve for just v, not v prime, not v double prime, just v. So to do that, we need to take the integral. And we're going to do it with respect to t because it's a function of t. So we take the integral, and then we get v prime equals k1, and that's what we're going to call our constant. Now we need to take the integral again, that's a tongue twister. And then you get v equals k1t plus k2. So k is our constant for now. Right? And now we're going to plug this equation back into our y2. And there it is. And then we're going to distribute our e to the 5t throughout. And there you go. And notice here, k2 to the k2 times e to the 5t looks pretty similar to c1 e to the 5t. So this is just another way of saying this. These are both constants. So we already have this term. This is what we needed. This is what needed to go into our equation. This was the second part that we were missing. So our final solution is going to be this. C1 e to the 5t plus C2t, this is where the t came from, e to the 5t. And do you have to do reduction of orders every time? No. I wrote it out in steps just to make it a little bit easier, and it is as easy as this looks. So first thing you do is put it into the characteristic equation. You're going to solve for r, and if r is being repeated, you put the first r into the e to the rt, and then write it again with the c1, and then this one's c2, and then you're just multiplying by t, and then that's your solution. Right? Now let's go to case 3. So now we're dealing with complex roots. So just notice how we have an alpha and we have a beta. It's also in our general solution. And what this is derived from is called Euler's formula. But he came up with this equation, and now we're using it in our solution for our second order differential equations. So I picked this equation out. It's y double prime plus 6y prime plus 10y equals 0. All right, so first things first, we're going to have to do our characteristic equation. And there's no way we can factor this. Whatever you try, it doesn't work. We're going to have to use the quadratic formula. So there it is in all its glory. So then we have r equals -6 plus or minus the square root of 6 squared minus 4 times 1 times 10 all over 2 times a, which is just 1. And then we can simplify it even further by saying -6 plus or minus the square root of -4 over 2. And we're going to simplify that even further by putting r equals -6 plus or minus 2i over 2. And when you just simplify that, you get r equals -3 plus or minus I. And notice how this is the same format as our r equals alpha plus or minus beta I. Our beta in this case is just 1. So our alpha is -3. So now all we got to do is plug this into this equation. And that is going to be here. So notice here's our alpha, and then our beta, which is just 1, is here. So this is the general solution of a complex root.